Okay, we got some past exam questions from exam 1 of fall 2021. Here's the answer key again. Here's the whole thing, in case you want it. Problem 1. The solution to the following mathematical operation should be correctly displayed as. So this is a sig fig question, and we are doing multiplication. When you do multiplication with sig figs, you just round to the lowest number of sig figs. So how many does this one have? This one is 5 sig figs. All of those are significant. And then the second number has 3. So we're just going to do this operation and then round down to 3 sig figs, because that's the lowest of the two numbers. And let's see, the full answer we get is 29.3972, and we're going to round that down to 3 sig figs, 24.4, and that leaves us with A. 2. Diamond made from elemental carbon has a density of that. What is the density expressed in units of grams per centimeter cubed? Okay, so we just got to do a unit conversion here. We are starting in kilograms per meter cubed, and they want grams per centimeter cubed. So let's just do some dimensional analysis. Okay, we're going to start with 3,500 kilograms, and that's in 1 meter cubed. Okay, so let's first go from kilograms to grams. In 1 kilogram, I'm going to put kilograms on the bottom so it cancels. I have 1,000 grams. And then now let's do the meters cubed into centimeters cubed, and they even tell us. Okay, in 1 meter cubed, we have 10 to the 6th centimeter cubed. Multiply all the numbers on the top and then divide by the ones at the bottom. 3,500 times 1,000 divided by 10 to the 6th. That gives us 3.5, and then kilograms canceled, meters cubed canceled. We have grams on the top, and then centimeter cubed on the bottom. So that leaves us with B. Diamonds are measured in carats. 1 carat equals 0.2 grams. The density of a diamond is that number. What is the volume of a 3.0 carat diamond? Another dimensional analysis problem. So they want the volume of a 3 carat diamond, and we know how many grams are in 1 carat, and we know the density. So let's first get how many grams are in a 3 carat diamond. So we have 3.0 carat, and we know that 1 carat equals 0.2 grams. So let's use this conversion factor. In 1 carat, there's 0.2 grams. I'm going to put carat on the bottom so that this cancels. 3 times 0.2 is 0.6, so 0.6 grams. And then we know we have another conversion factor of the density, which is 3.51 grams in 1 centimeter cubed. So then we know, I put grams on the bottom so that those cancel. 0.6 divided by 3.51, you get 0.171 centimeter cubed. That's a 3. Oops. Okay. And that is this one. 3B. How many neutrons does an atom of carbon-14 have? The number after they say carbon is the mass number. So whenever they do like element, and then a dash, what comes next is always the mass number. And the mass number, by definition, is protons plus neutrons. And also remember that a element is defined always by how many protons it has. So is there a periodic table down here? No, there's not. Okay, well, regardless, if you were to look at a periodic table, you'd see carbon has 6, where was I? Okay, if you were to look at a periodic table, you would know that carbon always has 6 protons. The elements are defined by how many protons they have. So, if carbon 14 has 6 protons, that means I know it has 14 minus 6 neutrons. So it has 8. You can just take the mass number minus how many protons you have to get the neutrons. So, in case it didn't really make sense what I just did there, I did mass number minus protons equals neutrons. I just minused over the protons and then got this. So 14 minus 6, we get 8. 4D. Which two of the atoms below have the same number of neutrons? Okay. Well, let's just solve for each one. So when we write in this notation of like EL is just some general element, this top number is the mass number, and then the bottom number is the atomic number. An atomic number is just number of protons, simply. So once again, if you take mass number and minus atomic number, which is the number of protons, you're going to get the number of neutrons. AKA, take this top number, subtract the bottom number, that's how many neutrons you have. So let's just go down the list and see how many neutrons we have for each one. 34 minus 16, this one is 18 neutrons. 32 minus 16, this one has 16 neutrons. 35 minus 17, this one is 18 neutrons. And then this last one has 20 neutrons. So which two have the same? Looks like this sulfur and then this chlorine. So that was sulfur 34 and chlorine 35, which is this one, I believe 5C. 6. Isotopes are atoms of the same element that differ in the number of neutrons. This one's kind of a knowledge question. Just, do you know what an isotope is? An isotope is the same element but different number of neutrons, or different mass number, which will give you this different number of neutrons. So for example, you can have chlorine 35 or chlorine 37. These both exist and they're both stable, but and because they're both chlorine, they have the same atomic number, but they have different mass numbers, and hence they have different number of neutrons. So that's just kind of the definition of what an isotope is. 7. What would be the formula for the atom or ion that contains 18 electrons, 16 protons, and 16 neutrons? So, step 1, what is 16 protons? We know elements are defined by how many protons they have. So, and the top number is the atomic number. Sorry, it's sideways, but yeah. So 16 is sulfur. So we know we got sulfur. And we also have 18 electrons. We have 2 more electrons than we do protons, and we know those are the only 2 subatomic particles that are contributing charge to our atom, and electrons are negatively charged. So if we have 2 more of them, this is going to have a 2 minus charge. So without even looking at, it's definitely not that, and we know it's not neutral, it's not any of these. So without even looking at the neutrons, I know it's A. And I lost the answer key. Okay. 8. Which of the following represents the formula for barium chloride? So let's first find these on our new and improved periodic table. So we got barium down here, that's a group 2 metal. And then chloride is a halogen. And we know that every element in this group has 2 plus charge, an ionic compound, 2 plus charge, and the halogens are 1 minus. So if we have barium 2 plus bonding with chlorine 1 minus, and we want to form a neutral atom or neutral molecule, because notice they don't have a charge, we're going to need to cancel the charges. In order to do that, we are going to need 2 of, I don't know why I wrote a parenthesis, we're going to need 2 of the chlorine atoms. So that leaves us with D. 9. After an atom has lost an electron, it becomes a, let's see. So, okay. After it loses an electron, electrons are negatively charged. After it loses one, the resulting nucleus will become a positively charged. And we know that positively charged ions are cations. My high school chemistry taught me that, a cation is positive, cat, right? Positive. In case you can't remember, anions are negative and cations are positive. There you go. That's stuck with me for 4 years, so in case you can't remember that, cations are positive. So we know this is cation, so we already know the answer is D. And positive. So 9D. 10. Sodium oxide combines violently with water. Which of the following gives the formula and bonding for sodium oxide? Let's go back to our periodic table. So let's find these. Let's use pink. Sodium right there. Group 1 metal, and oxygen non-metal, all the way over there on the right. So here we go. So when you bond a metal and a non-metal, what do you get? You get a ionic bond. And we also know that this sodium is going to have a 1+, and then the oxygen, we know it has 6 valence electrons, so it will require 2 more valence electrons, and it will essentially have a -2 charge. So one oxygen atom will require it will steal 2 electrons from the cation in this case. So in order to make a net neutral atom, we're going to need 2 sodiums for 1 oxygen. And we know it's ionic. So Na2O and ionic, which looks like C. Calcium hydroxide is used in mortar, plaster, and cement. What is its formula? Back to the periodic table. Let's go green. Calcium, group 2, so we know it's 2+. When it forms an ionic bond, which we're doing because hydroxide is a non-metal. And then hydroxide is always going to have a 1- charge. Reason being, let's see, oxygen, as I said in the last problem, has 6 valence electrons. Hydrogen has 1, but it only wants 1 more. These two are going to form a covalent bond right there, and then oxygen is going to need only 1 more electron to fill that hole to get its 8 valence electrons. So it's going to steal only 1. So it essentially has this 1- charge. So in order to make a neutral atom, we are going to need 2 of them per 1 calcium. So 2 hydroxides, 1 calcium, which leaves us with answer choice B. Oh, no, it doesn't. Okay, they got me. You got to put parentheses around it, because if you write it like this, if you write it like that, you're saying you only have 1 oxygen. So make sure you get the parentheses around it, which I actually wrote it like that. Do not fall for that trick. Make sure you have if you're writing like a molecule, like hydroxide is 2 elements, you got to make sure you put the parentheses around it. Because in case that explanation wasn't sufficient, when you write it in this form, you're essentially implying that oxygen only is a 1 there, which is not true. We want 2 hydroxides. So you're going to want to put the parentheses around it. 12. Which of the following has the largest number of oxygen atoms? Okay, this one is going to take some conversions. So we know Avogadro's number is 6.022 times 10 to the 23rd atoms per mole, per 1 mole. Let's see, what else are we going to need? We know molarity is equal to moles per liter. It's going to show up right here. And then we should be good. So I don't see a more efficient way to solve this problem than just brute forcing, checking how many oxygen atoms are in each one. So let's just do that. Let's start with A. Let's do some dimensional analysis. And this is O2. And in one, I'm going to take each one of these numbers. What I'm going to do, I'm going to take each one of these numbers and then convert it into just straight up oxygen atoms. And let's see here. So we want grams. So there are about 32 grams of O2 in 1 mole of O2. Reason I know that is the molecular weight of one oxygen is 15.99-ish, or basically 16. So O2 molecular weight is about 32 grams per mole. Okay, and in 1 mole of O2, there are 2 moles of oxygen atoms. I don't know why I said element. And in 1 mole of oxygen, there is Avogadro's number of atoms of them. Okay, let's throw that all in our calculator. Multiply the top, divide by the bottom. 1.75 times 2 times Avogadro's number divided by 32, and that's it. Okay, so this one, oh shoot, let me do a different color actually, we'll do blue. This one has 6.6-ish times 10 to the 22 atoms. This problem's going to take a minute. Okay, so we got A. Let's do B. We have that many molecules of C. Okay, this one will be quicker. 2.9 times 10 to the 24 molecules. Moles, it's carbon monoxide. And in 1 mole of carbon monoxide, there is 1 mole worth of oxygen, and in 1 mole of oxygen, we have 6.022 times 10 to the 23 atoms of oxygen. Okay, multiply the top, divide by the bottom. I got 1.75 times, oh, wow, that is way bigger. Did I do that right? Yeah, that looks right. Okay. So, as you can tell, that one's way bigger. Let's do C now. We have 1.5 moles of water, and in 1 mole of water, you have 1 mole of oxygen. 1 mole oxygen, you have Avogadro's number worth of atoms. It's supposed to say, oh shoot. It's supposed to say atoms. Okay. 1.5 times Avogadro's, and we have that many, a little over 9 times 10 to the 23. This is also atoms. Okay. B still seems like a clear choice. That's a different blue. Okay. Okay. D. Okay, D, 25 milliliters Okay, let's also, this is the molarity one, so, and we know molarity is moles per liter, so let's do this. In 1,000 milliliters, we have 1 liter, and we also know that, so keep track of this, so now we have liters, and we can multiply, molarity is moles per liter. So if I want to cancel the liters, I'm going to need to put 1 liter on the bottom and then 1.25 moles on top. So I'm using that molarity. The 1.25 moles per liter, that's what this is saying. So I'm going to use that as a conversion factor. And in let me also do this. And this is H2O2, hydrogen peroxide. In 1 mole of hydrogen peroxide, you have 2 moles worth of oxygen atoms, and in 1 mole of oxygen atoms, you have 6.022 times 10 to the 23rd atoms of oxygen. Multiply the top, divide by the bottom. Avogadro's number times 2 times 1.25 times 25 divided by 1,000. And we get 3.76 times 10 to the 22nd atoms. Okay. One more. Okay, we have 55 milligrams of CO2. Let's first make milligrams into grams because we're going to need to do molecular weight, which is always in grams. Well, typically 1,000 milligrams are in 1 gram. And the molecular weight of carbon dioxide, carbon is 12.01 plus oxygen is about 16 times 2. So the molecular weight of CO2 is about 44.01. I don't know why I wrote that there. Anyways, 44.01 grams per mole. Cancel that. Let's put grams on the bottom so that cancels. Grams, 1 mole, and that's CO2. And then in 1 mole of CO2, you have 2 moles of oxygen atoms, 1 mole oxygen atoms, Avogadro's number. Or in 1 mole of oxygen, you have Avogadro's number worth of oxygen atoms. Multiply the top, divide by the bottom. And I got 1.5 times 10 to the 21st-ish. So if we'll look at our answers, this one is by far the biggest, 12B. Okay. 13, which of the following... Oh, my God, another one. Wait, maybe this one will be easier. Okay. 13, which of the following contains the greatest number of atoms? Let's see here. Okay. In 1 mole of sulfur 8, octasulfur, whatever you want to call it, you have in 1 mole of S8, we're going to have 8 moles of sulfur atoms, and then in 1 mole of sulfur atoms, you're going to have Avogadro's number worth of the atoms. So for comparison, that's A. Let me set up B to illustrate this point. In 2 moles of P4, we're going to have, in 1 mole of P4, we have 4 moles of phosphorus. P is phosphorus. And in 1 mole of P, you that many atoms. So we look at these two, they're actually the same. I'm not even going to put in my calculator because this is, obviously those two are the same. The Avogadros are the same. These two are just going to be 8, and that's 8. So it's essentially 8 times Avogadro's number. So A and B are the same number. They have the same number of atoms. So it's not either of those two because they asked for the greatest. 4 moles of chlorine gas. Chlorine is diatomic. And if we have... actually, maybe it could be A or B. Looking at answer choice E. Anyways, let's just figure out what it actually is, I guess, and then we'll look at it. Chlorine is diatomic, and if we have 4 moles of it... Well, I guess I shouldn't erase my work. These two had 8 times Avogadro's number. They were the same. We know that. Chlorine gas, let's see here. 4 moles of chlorine gas in 1 mole. You have 2. Wow, they're all going to be the same. So they all have 8 times Avogadro's number worth. If I finish this is like 1 mole. Okay, well, I was almost tricked. They all have 8 times Avogadro's number worth of atoms. So you could tell just by looking at it. Also, you need to know here that chlorine is diatomic. It's a diatomic element, so when it's in its elemental form, it's going to form that chlorine 2. And you can just do the unit conversions to figure out that they're all going to have 8 times Avogadro's number worth of atoms. So 13D. Sodium bromate is used in a mixture which dissolves gold from its ores. Calculate the mass in grams of 4.68 moles of sodium bromate. Okay. So here, really all we need to do is figure out the molecular weight and then use that to convert moles into grams. Molecular weight is going to be grams per mole. So if we just take... I don't like red. Let me move out of red. Okay. I don't like that either. Okay. Molecular weight is grams per mole. So if we just end up multiplying by number of moles, we'll just get grams, which is what they want. So let's find that out. Let's find out what our grams per mole are going to be of this. We know we can find that out by adding the atomic mass of all the elements involved. So, molecular weight calculation, let's do that. Let's first get sodium. Where is it? Sodium right here, 22.990 grams per mole. I'm going to omit units. Bromine is, I just covered it up, 79.9. There's a lot of scrolling, sorry. And then we have 3 oxygen. Why did I do minus? That should be plus. Plus oxygen, which is 16-ish. It'll probably say 15.99. Yeah, I'm calling that 16. So you take the atomic masses, times it by however many there are. So in oxygen's case, that was 3. The other 2 were just 1. And then you add those up. So 3 times 16, 48, plus 79.9, plus 22.990, 150.89 grams per mole of this sodium bromate. I think they called it, bromate. So now we have that molecular weight. Let's do this. 4.68 moles. Let's put our moles in the denominator, so we can just do this. We can just multiply it straight across. Grams, and that is for 1 mole. So here's my molecular weight conversion factor. 4.68 times 150.89 700 and so moles cancel. 706.17 grams. And if you did sig figs, you'd probably get A. Not that sig figs matter, because obviously they're way different. So 14A. 15. A gallium-69 ion contains... So first of all, we know that the element tells us how many protons are in there. Always. One element will always have the same number of protons. So let's go up to, there it is. Gallium has its atomic number 31. So it has 31 protons. So nope, not you, not you. Okay. And we also know, so as was also mentioned earlier in this exam, whenever you have a dash number, like element dash number, it's this number that comes after the dash is always the mass number. I wrote that number mass number, not number mass. There we go. Okay. What comes after the dash is the mass number, and the mass number is protons plus neutrons. So if you want the number of neutrons, well, I'm spelling stuff wrong. Oops. If you want the number of neutrons, you can take mass number and then minus protons. So my neutrons is going to be 69 minus 31. I have 38 neutrons. I just did 69 minus 31. If I know I have 38 neutrons, not that one. Okay, so now we're down to B and E. We just got to find out the number of electrons. Protons have a +1 charge. Protons, they're +1. Electrons have a -1 charge. So if our element is +2 charged, that means it has 2 more protons than electrons, which leaves us with B. Because if we have 31 protons, it wouldn't make sense to have E, because if we had 33 electrons, that would mean we have a -2 charge, which we don't. We have a +2 charge. 16. The stable isotopes of neon are neon-20, neon-21, and neon-22. Neon-23, however, is radioactive. What is the most likely type of radioactive decay for neon-23? So first, I'll explain this without the band of stability and then with. So you perhaps don't really need it if... Let me just draw a picture of roughly what the band of stability looks like. Something like this. And we have protons on the X and then neutrons on the Y. So we know 20... also, let's figure out how many protons does neon have. That would be useful to know. 10. Okay. So, let's see. Neon-20 is 10 neutrons, 10 protons. And then we got 21, which is 11 neutrons, and then neon-22, which is 12 neutrons. And these are all stable. And if we were to plot them, let's just say they're somewhere like here. And as we go up, the 23rd, the neon-23 is going to be in this direction. And we're increasing neutrons. So neon-23, if all 3 of these are stable, they're near the line. And as we add another neutron, if it becomes unstable, that means it's above the line. So we know neon-23 is above the line. When we're above the line, to come back down, it's not very big. To come back down, we are going to take beta decay. So 16A. And also we can take a look at the band of stability to see if that corresponds the real one. So let's see here. If you were provided this on the test, you could just plot 10 protons and what was it, 13 neutrons. Yeah, so you can see that we're kind of above the line, and we would need to come back down. Anything in this region is going to experience beta decay. If we were below the line, down here is where you do positron, emission. How do you spell emission? Whatever. I've been doing this for a while. Electron capture. And then up in this region is, if you have too many protons, you do alpha decay. If you're really up high. Anything above 83 protons, so like that line-ish. If you're up in this region up here, you're going to do alpha decay. So those are the general 3 rules. In the case of this problem, it's definitely 16A, beta decay. 17. What happens to the mass number and the atomic number of a radioactive nuclide when it undergoes electron capture? Well, let's just take a look at an example. Let's do chlorine 35. And what are we doing? We're capturing an electron. An electron has a mass number of 0 and a charge of -1. And if we do this, we will get, what will we get? We'll get 16. What's still left of chlorine? I don't even know. Sulfur. Okay, so this is just an example of a change. The mass number did not change. We had 35 before, we have 35 after. So mass number decrease, that's not right. Okay, so does not help us too much. The atomic number did change. A is not true. Yeah, the atomic number decreased by 1, so we just know it's E. So I just set up a quick example here. I think illustrating some of the nuclear reactions can be helpful. If you just know that this is what an electron is, you can kind of just do an example and you figure it out pretty easily. So perhaps when you find problems, do a quick example. 18. That element, mass number 214, undergoes radioactive decay in a series of 4 steps to produce a stable nuclide Z. The series of steps, as shown below, involves a consecutive emission of an alpha particle, a beta particle, and another alpha particle. Which one of the following is the correct identity of the following stable nuclide? Okay, wonderful. So let's just brute force this and do all the reactions. So I'm going to, for the sake of not flipping back, I'm just going to have the periodic table open on my computer so I can just, I don't want to scroll on the iPad constantly. So PO, I'm looking for it. Okay, PO is number 84. Okay, that's too big. I'm gonna make this small for this problem. PO is 84. If you have a periodic table open, you look at atomic number 84, that's what PO is. And I know an alpha particle is 4 and 2. It is mass number 4, atomic number 2. So then Q is going to be equal to, if we just balance this, 210 and 82. So we know we can just balance these top equations. So 214 minus 4 is the mass number, 210, and then 84 minus 2 is going to be the atomic number. So Q is an atomic number 82. Now let's do this one. This is 0 minus 1. If we balance this now, we know X, maybe I should write this out. Okay, so we have 210, 82, Q equals X plus 0 and -1 beta. X equals, if we balance this, mass number is not going to, actually, let me just, okay, I'll do this. Okay, mass number is not going to change, and then it will have 83. So that's what X is going to become. Let me erase, oh shoot. So that's what X is. If we start our next problem with that, 210, 83, X equals Y. We emitted another beta particle. Y then is going to equal mass number, once again, does not change. Atomic number is going to go up by 1. So 21084. And then let's start with that. Equals Z plus 4, 2. We know an alpha particle is mass number 4, atomic number 2. If we balance this, Z is going to be 206 and then 82. Okay, and then now, obviously, the element isn't actually Z. So I'm going to look on the periodic table to see what corresponds to atomic number 82, and it is lead, Pb. So we have lead 206, which is C. What are we on? 18? 18C. So here, I just balanced each reaction. I know an alpha particle is always mass number 4, atomic number 2, and then these beta minus particles are going to be 0, -1. And then I just use those to keep balancing and iterating through all the steps until I got to the final answer. 19. Neutron bombardment of uranium-235 can induce the nuclear reaction given below. The product nuclide X is... So we just got to balance this whole reaction here. Let's do the top first. 235 plus 1 equals 141 plus 3 times 1 plus X. And let's see, X is going to be 236 minus 144. So X equals 92. And then let's do the bottom. 92 plus 0 equals 55 plus 3 times 0 plus X. Now let me not use the same variable. Plus Y. Y equals 92 minus 55. So when I wrote X here, I just meant the mass number. It might have been a little confusing how I wrote that. But I know my mass number now is 92, atomic number 37. I'm going to go back to my periodic table. The number that corresponds to atomic number 37 is Rb. So we got Rb30 or Rb92. And that has 37 protons. So D, 19D. Nice. Copper 62 is used in positron emission tomography to image blood flow in the body. Which of the following nuclides is produced when copper 62 undergoes positron emission? Simplest way to solve this one is probably just set up the example and balance it. So we got copper 62, and we are undergoing positron emission, which has the +1 in the bottom. And let's see, what is the atomic number of copper? I got a periodic table open. It's 29. So if we just balance this, the top number is going to be the same, and then this is going to be 28. The element that corresponds to 28 is nickel, the atomic number that is. So we got nickel 62 is our final answer, D. So I did this just by setting up an equation. I know these two, and then I can just balance to solve for this. 21. Magnesium 28 undergoes beta decay with half-life of 21 hours. If a sample of magnesium 28 initially contains exactly 10,000 atoms of the magnesium 28, calculate the number of atoms that are left after a week. Half-life problem. When we do half-life problems, we have two equations. We have that the natural log of the amount of atoms after some time divided by the initial amount of atoms. So this is the amount of atoms after some time t, and then this is the initial amount, and that is equal to negative times the rate constant k times the amount of time that we're undergoing. The second equation is the natural log of 2 equals the rate constant times the half-life. Okay. So here we are solving for the number of atoms that remain after 1 week, so it's going to be N. So generally the way these problems are set up is if what we're looking for is in the first equation, we're going to have to solve for the second equation first, probably get the rate constant, and then plug that into the first equation to solve it. So let's just start plugging stuff in and see where that takes us. Let's solve 2 first. So when we solve 2, we're going to get the natural log of 2 over the half-life equals K, and that's going to be equal to, the half-life is 21 hours. Natural log of 2 divided by 21 is 0.033, and this half-life was in hours. So this is reciprocal hours. Let's keep track of that, because they're gonna try to pull a fast one here. They want how many are after 1 week. So they want the final time unit to be in weeks, or we just have an inconsistency with our time units here. So let's be aware of that. Now that we have K, now we can solve 1. So let's see here. Natural log N is what we're solving for, so I'm going to leave that as unknown. N naught is how many there are initially, which is 10,000. They tell us that. And that is equal to negative the rate constant times the time. Now here we go. Okay, they want the atoms that are left after 1 week. But the units on our rate constant are 1 over hours. So we're going to have to times this by something that's just hours. Let's convert 1 week into hours. So in 1 week, I know there's 7 days, and in 1 day, I know there's 24 hours. Maybe you know what this number is off the top of your head. I don't, so I'm just going to convert this. So let's see, the weeks would cancel, the days would cancel. Yeah, there's 168 hours in 1 week. So I just did 24 times 7. So we're looking for 168 hours. 168 times 0.033. And then we are going to times that by -1. And I'm going to raise that. I'm going to take e to that power, because we have a natural log, times over 10,000. I'm just evaluating the algebra of this. I'm sure you can do that. And I get n equals 39.1. So, which that leaves us with B. 21B. 22. Rubidium-86 undergoes beta decay. A blank mole sample of rubidium-86 emits that many beta particles in 1 hour. Calculate the half-life for this atom. Okay. Same equations as before. Natural log of the atoms finally over the atoms initially equals negative times rate constant. Negative rate constant times time. And then the second one is the natural log of 2 equals the rate constant times half-life. Did I write that right up here? Yeah, I did. Okay. So those are our 2 equations. They want the half-life, which is in this equation, which means we're probably going to have to solve the first one first. Okay, so let's see. Yeah, we don't know K right away, so we're going to have to solve that using the first equation. So let's go green. If we solve this first equation, okay. So we're going to have to evaluate what N and N naught are. So let's see. Initially, our sample is this big, and that's in moles. But we know how fast it emits beta particles. We know that in 1 hour, it's going to emit that many particles, which means it's going to be that many particles smaller. So I can make 1 hour my T, and then I can take my N naught and then subtract off how many particles it loses to be my N. Okay, that might sound a little confusing, but we can just set T to be 1 hour, and then we can calculate how many particles we have left after an hour. So first, okay, a little confusing. First step, let's convert this moles into atoms. Because we are given a rate of emitting particles and not moles. So let's get this into particles. I know in 1 mole there is an Avogadro's number worth of particles slash atoms. I'm going to call them atoms here, so I think that makes more sense. 9.25 times 10 to the negative 5 times Avogadro's number. So we have, initially we have 5.73 times 10 to the 19 atoms. And I know the rate at which they're leaving. So after 1 hour, I will have lost this many particles. So I know that my n is going to be equal to 5.573 times 10 to the 19 minus 8.87 times 10 to the 16th. Because that's how many particles I'm losing, which equals 5.724 times 10 to the 19th. Okay, so a little bit messy. This is my n. This is my n naught. This is how many. The bottom one is how many we have initially, which is a little bit more than how much we have after 1 hour, which makes sense because it's not decaying that fast. So let's throw these in here. We got 5.724 times 10 to the 19 all over 5.73 times 10 to the 19. Divide these. Oh, and that equals negative k, and then we set the time equal to 1 hour. So if we solve for k, I get negative k is equal to negative 0.00155. K is equal to 0.00155. Okay, I have k. Now let's solve equation 2. They want the half-life. The natural log of 2 is equal to k times the half-life. So if I want the half-life, I can just do natural log of 2 over k, which is equal to the natural log of 2 over 0.00155. Natural log of 2 divided by that number, I get t half is equal to 447.6. No, actually 0.7. And the units are hours. Because I didn't track the units in this problem, but this one right here was 1 hour, which made this into hours. Yes. Or is that reciprocal hours? Anyways, it's hours. I'm not going to beat that over the head. 22C. 23. Calculate the age in years of a rock sample if 75% of the original amount of thorium contained in the rock has undergone radioactive decay. The half-life is that number. Okay, so 75% of the original amount has decayed, which means 25% remains. So if 25% remains, I know that n over n naught equals 0.25. Just a quick little note, because I think that's where you're going to, if you were to get this one wrong, that's where you do it. Let's take a reminder of our equations. Natural log of n over n naught equals negative kt. And the natural log of 2 equals k times the half-life. Okay. So we know from reading this part right here, 75% has decayed. If 75% has decayed, we know 25% remains. And percentage remaining is the same thing as saying the ratio of what is there now compared to what was there initially. AKA, this ratio, which is what we're going to plug into the parentheses. So, and we want the age, which is going to be t. So we're probably going to have to solve equation 2 first to get our rate constant. So let's do that. Let's solve for our rate constant first. 2. Equation 2, we're going to have natural log of 2 over the half-life, which they tell us is 1.4 times 10 to the 10th years. So k is equal to natural log of 2 divided by 1.4 times 10 to the 10. K is equal to 4.951 times 10 to the negative 11th. Okay, there we go. We got K. Now we can go on to equation 1. Natural log of 0.25, which we noted earlier because we know 25% is remaining. So we know that's 0.25 in the parentheses. And that equals negative the rate constant we just calculated. Also, this is in reciprocal years. Plug this in. Times some time that we're solving for. If we divide, now we can just solve this algebraically. The natural log of 0.25 gives me 1.39. Let me just, okay, so then t equals negative 1.386. If you put the natural log of 0.25 in your calculator, that's what you get. And then you divide over this term. Let's see, and then this is reciprocal years. Oh. So if you were to check the units, the years would flip up and t is in years. Anyways, that might have been, explaining the unit might have been a little confusing there. The units check out, we get years. And when you solve this, you're going to take your negative 1.386 divided by 4.95, and you get 2.8 times 10 to the 10 years. It's our final answer, which looks like D. 23D. 24. Naturally occurring uranium contains 0.005% uranium-234, a slightly higher percentage of uranium-235, and almost entirely uranium-238. In order to be used as fuel in a fission power plant, the uranium must be enriched to a slightly higher amount of uranium-235. This is because. So here is just kind of a knowledge question about how much do you know about the nuclear fission reactions and the reactors. The first thing is uranium-235 is always the fuel. Is it 92? I think it's uranium. Where am I looking? Yeah, uranium has atomic number 92. I was just checking that. I got a periodic table open. Okay, anyways, this is always your fuel in the nuclear fission reactions. And some other facts I know that will become useful is when they say the moderator, it's usually water or an isotope of water. I also attached this over here. So in case you want to pause and read this, this is on, I also attached the page of the textbook. This one's kind of a knowledge question. I don't know how much there is for me to explain here other than just kind of knowing how this works. The moderator is water though. So anyways, we know what the fuel is, we know what the moderator is. Let's read some of these answer choices and see if we can process of elimination it. Answer choice A, uranium-238 undergoes fission too easily. That's not true. 235 is the fuel, and that's what undergoes fission. So A is definitely not true. B, the amount of uranium-235 in naturally occurring uranium is too low to sustain fission. That's true. You do need to enrich it to be able to sustain the chain reactions. So B is the right answer. Let's keep looking at C and D to see if anything sticks out. In case you didn't recognize B as the right answer. C, uranium-235 also functions as the moderator. That's just not true. That's what water does. And D, uranium-235 reduces the number of neutrons colliding with the fuel, thereby controlling the chain reactions. Well, this one doesn't really make sense because it says it reduces the number of neutrons colliding with the fuel, but uranium-235 is the fuel. So B is the best choice. This one's just a little bit of specific knowledge questions. If you want to make sure you're good on this question, if you get the exact one, maybe read around there in the book. Or just read this little graph I pulled. Anyways. Question 25. That element that I'm not going to attempt to even name is a fictional element mined on Pandora that undergoes the following fission reaction after neutron capture. What are the atomic and mass numbers of this element? Okay, so here we just got to balance this equation. We know in nuclear reactions and their equations, we can balance the top row and solve for the mass number of the unknown element, and then do the same thing for the bottom row and solve for the atomic number. I'm going to call this A. I'm going to call this B. Let's solve for A first. A plus, that's not the same color. A plus 1 equals 105 plus 146 plus 3 times 1. A equals... I'm too far in. I'm not even going to try. Don't make fun of me. A equals 253. B plus 0 equals 53 plus 57 plus 3 times 0. B equals 110. So we have a mass number equal to 253. Atomic number equal to 110. Let's see. Okay, and that leaves us with answer choice D, 25D. Good. 26. Sodium-23 is formed by the beta plus decay of which of the following isotopes? When you get questions like this, I think it's just easiest to set up the example and literally solve and balance the reaction. So they say sodium-23 is formed, so we know it's a product. And sodium is what, 11? It's atomic number 11, so I just filled that in. And let's see, we're undergoing positron emission or beta plus decay. So the right-hand side is going to look like this, because I know that this positron is being emitted, and I know we are forming sodium-23, and sodium is an atomic number 11. Okay, so now, if I only have one element on the left-hand side of the equation, what's it going to be? If I balance these top, I know it has to have a mass number 23, and if I balance the bottom, it has to have atomic number 12. Looking at the periodic table, atomic number 12 corresponds to magnesium. I have it open on my laptop, by the way. I unfortunately don't just know all these. Anyways, magnesium-23 is the answer. A. 26A. 27. Which of the following nuclides would you predict to be the most stable? Okay, stability of atoms. Here, let's do this. We got the band of stability. I'm not going to name it. I don't know why I was going to do that. Okay. Protons on the X and neutrons on the Y. Okay, so let's see. We could, the rigorous way to do this, well, first of all, hold on. First of all, let me go through and kind of label all these. They tell us the mass number of them, but we don't know the atomic number, which is going to be useful. So I'm just going to go down the list on my periodic table and write all these down. Potassium is a group 1 element. It has 19 protons. Argon, that's a noble gas. That's got 18. PD, what is that, palladium? Palladium is kind of in the middle of the periodic table. It's a transition metal. It's got 46. AM, that's F block. Americium, sick, 95. That's all down the bottom. That one's, not very common. Nitrogen, can't say the same for that one. That one's 7. Okay, so that's how many protons all these have. I just pulled this off the periodic table. And I also know that mass number minus atomic number equals number of neutrons. It will be useful to know how many neutrons each of these have for the sake of plotting them on this graph. So let me just also figure that out real quick. 55 minus 19, 36 neutrons, 32 minus 18, 14 neutrons, 92 minus 46, 46 neutrons, 243 minus 95. 148 neutrons and 7 neutrons. Okay. So, let's see. What does the band of stability look like? Now, if I had all the time in the world, or if I was given the band of stability, where is it? I know we used it earlier. Okay. I would just take this, and if they gave me a very specific one with numbers, I would just plot. Let's get rid of my mess first. I would just plot every single one of these elements. And see which one fits on the line. Because if it's going to be on these black dots, these are stable, right? And anything that might be off over here or over here is not stable. So, but let's pretend we don't have that real quick, so you can still solve this problem without it. And, maybe they don't give it to you. So, we know roughly what the band of stability looks like. It follows a rough 1-to-1 trend, and then, it looks bad. Oops. Okay. It follows a rough 1-to-1 trend and then slopes up. So, we can kind of just predict where stuff's going to be at. And also, we know that anything in this region will move closer to the band of stability through beta decay, and then you can do electron capture and positron emission if you're down there. But you can also do alpha decay up here. So anything, and I know I'm mentioning this because one of the answer choices stuck out. Anything with if your atomic number is greater than 82 or 83, I know I mentioned it in the nuclear chem video. If it's greater than 82 or 83, you're going to undergo that alpha decay. So immediately I'm looking at americium and I'm saying no way. Because it's too big, it's probably going to undergo alpha decay. Okay, let's real quick plot the rest of these. I know I'm already spending a lot of time on this. Okay, A, we have 19 protons and 36 neutrons. That's way off a 1-to-1 ratio, so that one would be like up here. Argon has more protons than it has neutrons, which is definitely not near the 1-to-1 line, so that would be below. Because the 1-to-1 line is if it's same number of neutrons and protons. These two are unlikely to be true. Lead, or no, not lead. Palladium has the 1-to-1 ratio, but it's bigger. It has 46 protons. So then you're getting up into these regions where if you projected that perfect 1-to-1 ratio, it'd still be good, but it still slopes up. And if we look at answer choice E, nitrogen is a very small molecule. It's a very small molecule. It only has 7 protons, which means we're way down at the left, and it has 7 to 7, which means in this early region, when the band of stability is the 1-to-1 ratio, nitrogen fits in there perfectly. So it's very stable. So the correct answer choice is definitely E. I'm going to add some extra remarks here. So that sounded, perhaps if you're given the band of stability, just go through and plot all of these instead of kind of speculating like I did. And it'll be very obvious. You won't have to guess at all. Also, I know that the atomic mass of nitrogen is it's 14.007, which means it's nearly exactly 14, which means the nitrogen 14 isotope is overwhelmingly abundant. I suppose you could interpret that other ways, but generally that means the nitrogen 14 isotope is extremely abundant. And if you kind of just know that, the atomic mass of nitrogen is 14, then you know that nitrogen 14 is going to be very stable. Anyways, a couple ways to get to this. You can kind of just know the general trend of the band of stability. You could plot every single one exactly if they give you this. And you also have to know that 95 is too big and you'll undergo alpha decay. couple things to think about here, but yeah, 27. E. 28. What is Rn? Let me look at this. Radon? No. Okay. Radon-222 decays by alpha decay, and the resulting nuclide can further decay by either alpha decay or beta minus decay. Which two isotopes result from radon-222 after 2 disintegration steps? Okay, so we have a 2-step process here, but we know the first one is always going to be the same. So let's write this way. We have the first step, and we'll do the second step, which is going to have 2 options. So let's see, we got radon-222, and we know that this is undergoing alpha decay first. An alpha particle is a mass number 4, atomic number 2. Now, if we balance this, we're going to get 218 and 84. The element that is 84 is polonium. It's PO. Okay, so now this PO is going to be our reactant for either of the next 2 steps. And we can do alpha decay again, or we can do beta minus decay. So let's set both of these scenarios up. This is our reactant for each one. Let's see. Let's do alpha decay first. So if you do alpha decay again, you got 214, 82. The element that is 82 is lead, which is Pb. So here's our first answer. If you do alpha decay twice, that's your answer. Now let's check if you alpha decay and then beta minus decay. Same starting reactant. This is our beta particle. They say it's minus, so it's -1 on the bottom. Add on, oh wait, let's balance this. Mass number doesn't change, and this is going to be 85. The element that corresponds to 85, it's AT, astatine? Astatine. Okay, so we got 214 lead and 218 astatine. Which, let's see, no, looks like B, 28B, 28B. 29. If a sample of radioactive isotope undergoes positron emission and has a half-life of 1 day, at the end of the 3rd day, blank of the original sample will be left, and the atoms that decay will now be atoms of a different blank. A half-life is a unit of time. Its half-life is how long it takes to lose half of its material. And if you want to know, how much is left after X days, you can just do half. And then to the exponent of the number of days. Let's see here. So after 3 days, this would be 1/8 would be left. In case that's not obvious, we know simply that it's losing half of its life every day. So initially, say we have 1 unit of sample. I don't know. We have 1 unit of sample. After 1 day, we'll be down to half a unit. After the 2nd day, you'll be down to 1/4. And after the third day, you'd be down to 1/8. You're halving it every day for 3 days. That'll get you down to 1/8. And let's see, the atoms will be of a different, and we're doing positron emission. So let's just take a look. They want to know whether it'll be a different isotope, aka just change the mass number, or a different element if we change the atomic number. So let's just balance an example equation. Common element chlorine 35. If it undergoes positron emission, that will look like this. And if we balance this, this will be 16, 35, and the 16th element is sulfur. So if we look at this now, chlorine is not the same element as sulfur. They have different protons. So the element does change. They are of different element. So 1/8 an element, B, 29B. A rock contains 150 millimoles of uranium-238 with that half-life and 220 millimoles of lead-206. Assuming all the lead-206 comes from the decay of uranium-238, estimate the rock's age. Okay. Well, we know we have two equations associated with half-life and how we solve all these problems. Natural log of n over n naught equals negative rate constant times time. That's the first one. The second one is the natural log of 2 equals rate constant times the half-life. Okay. They want the rock's age, which is going to be T. So we're going to have to figure out the rate constant from equation 2 and then figure out what n over n naught is. Let's solve for the rate constant first. So if we evaluate 2, we're going to get natural log of 2 over the half-life, which is 4.5 times 10 to the 9 years is equal to the half-life. Wait, no, that's equal to K. Oops. Which is equal to natural log of 2 divided by 4.5 times 10 to the 9th. 1.54 times 10 to the negative 10. And that's reciprocal years. Okay, so there's K. Now we need to get n over n naught, where n is the number of moles or atoms or particles left after some time, which is the age, and then n naught is going to be the initial amount. Let's do a different color. Let's do purple. So n is going to be equal to how much is left after some time. This is going to be our 150 millimoles. Because time t equals 0 is like when the rock is first, spawned into existence. That's time t equals 0. And then the age is now the amount of time that has passed from that point. And at that point, which is present, we have this many millimoles of the uranium-238. Initially, at the time like t equals 0, we know that all the 220 millimoles that exist within the rock of the lead, they say that all of them came from uranium-238 at one point. So initially, we had 150 millimoles plus 220 millimoles of the uranium-238. So initially, we had 370 millimoles. So our N is 150, and then our initial is 370. Now, if we solve equation number 2, we know natural log of 150 millimole over 370 millimole. This obviously is just going to cancel. That's going to equal negative. We have our rate constant because we solved for it. Reciprocal years times the time, which is what we're solving for, in years. Okay, and the units check out. So, natural log of 150 over 370 is negative 0.9. We're going to divide over the 1.54 times 10 to the negative 10th. You get T equals 586153200. That is 5 billion. 5.86 times 10 to the 9th. Yeah, so that's our answer. And that looks like C, 30C. 31. The mass of a helium-3 atom is... Okay, now we're getting into the relationship between energy and mass. Okay, which we're going to need a graph for. Okay, I put some info here. Okay, first let's map what these are. So a helium-3 atom, I'm going to use blue for a proton and green for a neutron. It is mass number 3, which means it is 1 neutron and then 2 protons. A hydrogen-3 atom has 1 proton and 2 neutrons. So they don't actually have the same makeup. And let's see, I put this here. A proton and a neutron don't have the same mass, which means this is probably not the same, because they have different makeups of subatomic particles. Okay. B through D, on the other hand, these are 2 hydrogen atoms, which would just be the 2 protons, and then 1 neutron. So just separated out, floating in space. Okay, they actually all B through D all talk about this system. So now we're comparing the instance when these 3 subatomic particles are in a nucleus, as opposed to when they're just flying around unbonded. We know that as these we just know this. This is just kind of a piece of information you have to know. When they form nucleuses, the mass decreases. And hopefully, let's see. I know it. Yeah, we have this down here. So we know the mass decreases. So you kind of should just know from your knowledge that the mass of a helium-3 atom is going to be slightly less. It's going to be slightly less than the unbinded addition of those subatomic particles. So you kind of should just know from your knowledge that 31 is going to be B. Also, I think this, yeah, I was looking at this earlier. This is the binding energy graph is also a decent representation. We know that, I think it's very intuitive to think about. We know that, let's see, fission, it moves this way, fusion moves this way. When you think of, say, like a nuclear reactor or an atomic bomb, we know that this process releases a ton of energy. So does this process. And we know that delta E equals delta mc squared. So if you are releasing a ton of energy out of your system, your mass also has to go down. So I think it's kind of intuitive to think as you move this way on the graph, your mass is decreasing because you're releasing a ton of energy. Same thing, fusion is the exact same way. So on this graph, these are the energies, these are the higher masses, the endpoints are the higher masses, and this point is going to be your lower mass. I think it's kind of an intuitive way to think about it. And when we compare them, yeah, they even have the hydrogen-3 and the helium-3. So hydrogen-3 is higher up, which means it is lower mass. Okay. So yeah, we could also look at the graph to figure that out, that A is not the right choice. And we just know that as atoms form, as the subatomic particles form nucleuses, they lower their mass, always. Always, always, always. So, B. 32. Which of the following statements are true when a heavy element undergoes fission? A. There are fewer nucleons after the reaction than before. That's definitely not true. All the nuclear reactions still have to be balanced. B. There is less mass in the same number of nucleons. If you watch the explanation of the previous problem, I was kind of going on about that. But yes, this is absolutely true. Let me go back. Let me give the exact same explanation. So it doesn't show it here, but fission takes, well, imagine uranium-235, and it moves it in this direction because this is the most stable nuclide, and it even says it. As you can imagine, well, we know this relationship. we know that delta E equals delta MC squared. Picture an atomic bomb or a nuclear reactor that releases a ton of energy, and that huge energy release lowers your energy of your system. And by this relationship, you have to lower your mass. So fission lowers the mass. And it's the exact same deal. They don't ask about it here, but it's the exact same deal for fusion. So 32, there is less mass and the same number of nucleons. That is true. C, there is more mass. No, that would imply that we are absorbing energy during fission, which is certainly not the case. D, there is more nucleons. We don't create or destroy nucleons. All the nuclear reactions are balanced, so it's not D. 32B. Which of the following nuclides is most likely to undergo fusion to form a more stable nuclide or nuclides? Refer to the figure below. The further you go on the endpoints, the less stable you are. So, let's see. Okay, wait. Fusion. So, okay, first of all, what is fusion? Fusion is, fusing together. So you can imagine two smaller particles that are coming together. That's an arrow. Oops. That are coming together to form one bigger atom. So they are fusing together. And fusion occurs on this side because these are the smaller atoms. So generally it's going to be things with atomic numbers less than 60. If we look at the answers, gallium has greater than 70. Wait, this is mass number. Oops. Let's see. That is mass number. Okay, we're good. So if gallium has a mass number 70, let me do pink. Okay, gallium. They're proposing gallium with mass number 70. That would be right here, and this is in the fusion region or fission region. Anything on this right hand side would prefer fission. NB, whatever it is, I don't even care because it's over here. It's to the right, not that one. PD, palladium 106, once again, it's over in this region. And then 209. These four choices are all over here, which are all going to do fission. The calcium is the only one that is to the left-hand side. It's the only one small enough that would do fission. 33A. Or fusion. It's the only one that would do fusion. Fusion is where you come together, and that's what they're asking about. 33A. 34, okay, we're getting into, what is this, limiting reagent problems? 34, how many moles of carbon dioxide are produced by the combustion of 227 grams of butane in excess oxygen? Not a limiting reagent problem because we have excess oxygen. This one is going to be, do you know Stoich? Let's see. Oh, and they tell us, look, it's unbalanced. Okay, let's balance this first. Let's see, carbon is going to be, it's available in the least species, so I'm going to balance it first. I have 4 carbons on the left-hand side. I'm going to put a 4 there to get 4 carbons on the right-hand side. That gives me, what do I do? Okay, we'll do oxygen next. No, we'll do oxygen last. Hydrogens, I have 10 on the left-hand side. Let's get 10 on the right-hand side. I'm going to put a 5 there. Then that constrains me on the right-hand side. I have 8 O2 coming from that, and I have 5 O coming from, I have 8 O. Oops. I have 8 O coming from carbon dioxide, and then 5 O coming from the water. So I have 13 oxygen on the right-hand side. Okay, and our oxygen is in factors of 2, which means I couldn't just put a 6 or a 7. If I did a 6, I would get 12 O2s on the left-hand side. If I did 7, I'd get 14. So we got to times everything by 2, and then this is going to become 13, I think. I'm just guessing here. Let's see if I did that right. Okay, I times what we were going to do by 2. Okay, so I have 8 carbons on the left. I have 8 carbons on the right. I have 20 hydrogens on the left. I have 20 hydrogens on the right. I have 16 O's, and then I have 10 O's, which gives me 26, and I have 26 O's on the left-hand side. Okay. Equation is balanced. Now let's just do stoic. They want moles of carbon dioxide produced if we have 227 grams of butane. Let's first get the molecular weight of butane. Carbon is 12.01 grams per mole. And hydrogen is 1.008. That's an 8. 8 grams per mole. And in one butane, we have 4 carbons and 10 hydrogens. So the molecular weight of this molecule is 4 times 12.01 plus 10 times 1.008. The molecular weight of this molecule then 48.04 plus 4 times 12.01 plus 10 times 1.008, 58.12 grams per mole. Now we should have everything we need to solve. Let's set up our dimensional analysis. So that's what we're starting with. We know we have 227 grams of butane in, and there are 58.12 grams of butane in 1 mole of butane. And reacting, we have 2 moles of butane for 8 moles of carbon dioxide. So let's use that. 2 moles of butane is going to yield me 8 moles of carbon dioxide. What do they want? Okay, they just want moles of carbon dioxide produced, so we're good. I was about to set up one last one for grams, but this is the unit they want. They want moles of CO2 produced, so we're good. Multiply the top, divide by the bottom. 8 times 227 divided by 58.12 divided by 2. I got 15.622 moles of CO2 produced, which is C34C. Good. 35. What is the change in internal energy of a system that releases 775 joules of thermal energy to its surroundings and has 530 joules of work done on it? Oops. Actually, I'm not going to do that. Here's my system. It's a box. Okay. Here, this is just, can you read a word problem and interpret the words and verbs they use correctly? So, let's say this. The change in energy of my system is going to be what's coming in minus out. Let's see. It's releasing. This verb means energy's coming out. So 775 joules are coming out. And we have 530 joules of work done on it. When they say on it, I know it's coming in. So my delta E, I got 530 coming in. I got 775 going out. 530 minus 775. It's a delta. Equals negative 245 joules. These are all joules. 35D. 36. Athletic trainers carry cold packs when transporting ice is not possible. Cold pack temperatures are lowered when ammonium nitrate is dissolved in water. Which of the following is true about the dissolution process? So, okay. Here's my cold pack. And, let's see. It is cold, which means it is sucking in heat from the outside, which means it is endothermic. This process is sucking heat into the system, which is making it colder, which is then drawing in heat from the hotter surroundings. Heat flows from hot to cold, so the hot surroundings then are losing energy to this, making the air around it seem cold. So I know it's endothermic, and endothermic reactions have greater than 0 delta H's, which leaves me with D. Yeah. The reason that the delta H has to be greater than 0 is, I guess, just a piece of knowledge that you should know. Perhaps. 37. One piece of gold jewelry at 120 degrees Celsius has exactly 1/2 the mass of another piece, which is at 40. Both pieces are placed inside a calorimeter whose heat capacity is negligible. What is the final temperature inside the calorimeter? What you need to know here, first of all, Q equals mc delta T. And we know that when we're going to combine these, we know a couple things. When I combine the one piece of, gold? Yeah, gold jewelry. I'm going to combine one piece with the other slightly smaller piece. Eventually, they will reach a thermal equilibrium where their temperature final of the first piece equals the temperature final of the second piece. That's going to be one condition we need to know to solve this. The second noteworthy thing is that the heat gained by one has to be equal to the other. So this is kind of like a closed system. Nothing's coming in or leaving. Doesn't happen. So the heat gained by one is equal to the heat lost by the other one. So like that. So if we know this, we can just set the two mc delta t's of the two systems equal to each other and then solve. And also use this, which will make it from two unknowns into one unknown. So what does this look like? I think that might have been a little complicated, but I think if you see it, it'll make sense. Okay. M1, C1, delta T. I'm going to expand delta T into TF minus TI equals of 1 equals M2, C2, TF minus TI of 2. So I just wrote both of these out for each one. Now, they are both gold, and specific heat, C, is a property of a material. So C1 is equal to C2, and if you divide that out, those are just going to go away. Let's see here. Okay, so I'm going to ignore that in the next line. And I also know that one piece of gold jewelry is half the mass of another piece. The 120 degree one has half the mass. So M1, 2M1 equals M2. We're going to sub this in now. I'm getting rid of C1. I'm going to leave TF as TF. TI for the first one is 120. And let's see, I know M2 is equal to 2M1. I'm getting rid of C again. TF, and then let's see, the final temperature, or the initial temperature of this one is 40. Okay, so there's our final equation, and these two TFs we know are the same. So now we should have enough information to solve. Let me rewrite this over here and expand it. M1 TF minus 120 equals 2M1 TF minus 40. Okay. The M1s are going to cancel. You're going to get TF minus 120 equals 2TF minus 80. It's distributed. Let's see. TF equals negative 40. I definitely got a unit wrong. Oh, I see. I forgot this negative. There should be a negative in front of this, negative in front of that. This becomes negative. That becomes negative. That becomes positive. Which then changes my final answer into 3T. Oh, God. Oops, change color. 3TF equals 200. TF equals approximately 68. Yeah, okay, so let me actually do this. It's not approximately 68. It is, so 200 divided by 3, 66.67, aka 67. Okay, this one might have been a little bit confusing. The important takeaways here is I know the heat gained by one is equal to the heat lost by the other. So I can set this up. And don't forget to put the negative in front. That's why mine went wrong. And even if you do mess that up, you can catch yourself pretty easily because your temperature you should get for your final answer will be somewhere in between these two. If I'm combining something that's 120 degrees Celsius and 40 degrees Celsius, I know the final temperature has to be somewhere in between those two temperatures. So when I got negative 40, that didn't really make sense. So you know it has to be somewhere in between those. So, I mean, and even just using that rule, I know 160 can't be the answer. And then, so I know this. I know the heat gained by one is equal to the lost by the other one. I know the final temperatures are the same. And I can also set up a ratio of the masses to take the masses out of the equation. I know if they tell me the material is the same, since they're both gold, the specifics heat have to be the same, so I could divide those out. And then you can solve. 38. If you wish to warm your room by taking 10 kilograms of a heated substance at 99 degrees Celsius into it, which of the following would be the best choice? The specific heat capacity of each substance is given in the parentheses. Okay, so assuming my room is at about 23 degrees Celsius and I'm bringing in something that's hot and I want it to heat it as much as humanly possible, I want something that holds a ton of energy, or the most amount of energy possible. I want the most amount of energy per kilogram, because I'm only bringing in 10 kilograms. So I want the most amount of energy per kilogram. You can think about that as kind of joules per kilogram, or joules per gram, which is units we want. So we want the biggest number possible. We want the highest number possible of this, which would be the water. If you also were to set up kind of the equations like I had in the above, and you wanted to find the highest delta T, that would be perhaps another way of thinking about it. But you just want the most amount of energy. The water can carry the most amount of energy with it at that temperature. 39. A student in a lab combined that many grams of one. 39. A student in lab combined hydrochloric acid solution with sodium hydroxide solution in a coffee cup calorimeter and recorded the temperature data below. Calculate the enthalpy change per mole of hydrochloric acid. And they tell us the specific heat. Okay, so we are solving for the delta H of reaction, and they give us temperature data, and they want it on a per mole basis. Okay, so this is going to take two steps. One, we know delta H reaction is going to be in energy per mole. They say, okay, they want it in kilojoules per mole. So we're going to want to do two steps here. Let's first solve the energy released of this example, and then find how many moles are reacting. We're going to get kilojoules in the first step, and then the second step, right down here, we will get the moles of hydrochloric acid reacting, and then we're going to do what we get. We're going to get our answer from 1 and divide it by the answer from 2, and that should get our answer. So this one's kind of a two-step process. First, we're going to get the energy, and we're going to use that. We're going to get that by doing Q equals MC delta T. Let's start plugging stuff in. We're looking at the heat change of our entire system, so I'm going to use both masses since they're both in our system. So I'm going to do, for my mass, I'm going to do 41.514 plus 51.158. And if you do that, you'll get 92.672 grams for our mass. C is the specific heat, which they tell us is 4.184. and that's joules per gram per degree Kelvin. And then we have temperature change, which we can get from our temperature data. To get delta T, you're going to want to always do the final temp minus the initial temp. If you do that, you get 26.95 minus 20.39. You're going to get 6.56 degrees Celsius. But that was a change. So, okay, so let me also point out the units here. The difference between, if you take like a delta temperature like this, it doesn't matter if you're in Celsius or Kelvin, because the difference between Kelvin and, let me illustrate this. If you're the difference between Celsius and Kelvin is just the constant, which would get subtracted out. So let me illustrate this in case it's not obvious, but I guess you can just skip this if it is. So let's see, this is what it looks like in degrees Celsius. If I were to convert both of these to Kelvin, if I just add 273, here I'll do an orange above. This will give me 299.95, and then 20.39 plus 273, it's going to be 293.4. And this also is horrible handwriting. Let me redo that. 299.95. This orange is going to give me the same delta T as the one right below it in blue. Quick little note, that might have been a spot for confusion. I don't know. So, anyways, our delta T is 6.55 degrees. So our grams are going to cancel, our degrees units are going to cancel, and we're just going to be left with joules. Let's calculate this. Q is equal to 92.672 times 4.184 times 6.55. Q is going to be 2,539.7. Okay, so there is, and that's joules. And I believe that, yeah, the final answer wanted kilojoules. Let's convert this into kilojoules. Let me be rigorous. There are 1,000 joules in 1 kilojoule. Therefore, I know there are 2.5347 kilojoules. Okay, so there's our answer to the first step. We know how much heat is being released. Now let's figure out how many moles are reacting. And perhaps in another problem, you might not know what the limiting reactant is. You might have to set up a whole limiting reactant problem and solve for whether hydrochloric acid or sodium hydroxide would be the limiting reactant. But they tell us just to do per mole of hydrochloric acid. So I'm essentially just going to assume hydrochloric acid's the limiting reactant, more or less. Or they just tell us explicitly to do it that. So I'm going to figure out how many moles of hydrochloric acid are reacting. They give us 3 pieces of information. We have a mass of our solution. We have the concentration of our solution. And molarity is moles per liter. And they give us a density of grams per milliliter. And we want, so they also tell us that the density is 1 gram per 1 milliliter. So what we're going to want to solve for is moles, and we know this, so we just need to get liters. We can get liters. How could we get liters? We can get liters by timesing our density, timesing our mass by the reciprocal density. So we know we have 41.514 grams of the solution. And we know that the solution has 1.0 grams per 1 milliliter. That's my density. So I know it has, well, it's just one, that's 41.514 milliliters of volume. I'm going to convert this into liters real quick because that's what our molarity is in. I know there's 1,000 milliliters in 1 liter. So let's divide that by 1,000. which gives me 0.0415 liters. So now I have liters, and I know the molarity. So I know the molarity is 1, which is equal to the moles over the liters. So if I times over how many liters I have, I will get the moles. So 1 times 0.0415 equals how many moles we have. So we have 0.0415 moles. I just times the number of liters I have over. So now we have these two answers. We have this number of kilojoules and we have number of moles. I can just divide them. So let's do that over here. 2.5347 kilojoules divided by 0.0415 moles of hydrochloric acid reacting gives me 61.1 kilojoules per mole, which is, also I should mention the sign. So they're all negative, so I guess sign wouldn't really affect you here, but so that would lead you to E. Why is the sign negative? We know that the sign of our delta H of reaction tells us whether it's exothermic or endothermic. I know that the temperature of my system is increasing, which means this reaction is forcing it to release energy, which means it's exothermic. So, and I know exothermic reactions have negative delta H's. So it should be negative 61.3-ish. We were off by a little bit, but I'm sure I rounded a couple times. 40. A student in lab added calcium chloride dissolved in water to deionized water at some temperature in a coffee cup calorimeter. The max temperature measured in the calorimeter after addition of the solid was 26. So it heated up a bit. Calculate the delta H in kilojoules per mole for the dissolution of calcium chloride in water. Assume that the solution has the same specific heat as water. Okay, so same deal as before. Also, in case this notation is a little bit strange to you, that just means we have calcium chloride, the molecule, and it's dissolved. And for every one molecule of calcium chloride we have, there are 2 water dissolving it. And we are adding this already dissolved solution into another solution of deionized water. Okay, so just to perhaps paint the picture. So we're going to have to do this, we're going to have to solve this similarly to last problem. Let's first, let me get off pink. We're going to want to get the heat. We're going to want to get the number of kilojoules. Also, in case, I don't know, I always put the brackets around the equations. In case you don't know that just means units. I don't think I knew that freshman year. Anyways, heat, we're going to want kilojoules, which we are going to get via Q equals MC delta T. This is going to be equal to the mass of our whole system. So I'm going to add together the mass of the deionized water and our solution. So 49.03 plus 4.029. I'm using both because this is, when they're mixed together, both of them are in our system per se, and they're both changing the temperature. So I'm going to include both of them in my mass. It's grams. They tell us to use the same specific heat as water. 4.184 joules per gram per degree Kelvin. If you don't know that, it's also in the top problem. Times delta T. And our delta T is 26.2. It's our final temperature. Minus our initial temperature, which is 20.77. 5.43 degrees Celsius / Kelvin. Since it's a change, doesn't matter. Units, grams cancel, our temperature cancels, and we are left with 53.06 times 4.184 times 5.43. Q equals 1,205.5 joules. And they want kilojoules. This is 1.2055 kilojoules. Okay, step 1 good. Let's go into step 2. We're going to want to get the number of moles of the calcium chloride that's dissolved in water. We're going to want to get the number of moles of that we have, because they want the delta H for the dissolution of that species. So we're going to want the number of moles of that species, and we're going to include the water. So they give us how much of it we have. We know we have 4.029 grams. And since here we're not concerned with just one species, whereas in the last problem we had to go the long way around and get just hydrochloric acid, it's because this hydrochloric acid was dissolved in some solution, and we wanted it on per mole of the hydrochloric acid. But in this problem, we want the dissolution of this entire species, so we can just go straight from this mass and use a molecular weight, which is going to be moles per grams. We can just go straight from that into moles. So let's figure out the molecular weight of this species. We got, of calcium chloride 2, and then there's also 2 moles of water in there. So 2 molecules. So the molecular weight of this is going to look like, calcium is 40.078. Chlorine is 35.453, and we have 2 of them, so I'm going to multiply that by 2. And then we got 2 waters, so I'm going to do 2 times what is water. Water is 1.008, which is hydrogen, times 2 plus oxygen, which I'll just say 16. So let's get this molecular weight. First of all, what is 2 oxygens? I'm just going to call this 32 or 36. 1 water is about 18, so I'm just going to call that 36. 40.078 plus, there should be a plus in between these. Oops. 40.078 plus 35.453 gives me 75.531 plus 36. Oh, also, I forgot to times the 35.453 times 2. So, okay, 35.453 times 2 plus 40.078 plus my water, which is 36. I get a molecular weight of 146.98. So that is 146.98 grams in 1 mole. So now we can get the moles. 4.029 divided by 146.9. I get 0.0274 moles. So now we have kilojoules and we got moles. We can combine these. We can do 1.2055 kilojoules divided by 0.0274 moles. We get 44.98 kilojoules per mole. And that looks like D. Oh, wait, hold on. We should actually care about the unit. Hold on. So that could be B or D. And we want the delta H of this dissolution process. And we know that the temperature, let me clean up, this is a mess. Okay, we know initially the temperature is 20-ish, and it's finally at 26.2. It's heating up, therefore it is a exothermic process because it's releasing energy. That's why it's heating up. And I know all delta H processes that are exothermic have negative delta H's. 40B. 41. Choose the best answers to complete the following sentences based on the information given. When 50 milliliters of hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide are combined at room temp in a coffee cup calorimeter, the temperature of the resulting solution is higher than at room temp. And okay, this first one is, they're asking, is it exothermic or endothermic? If it's heating up, energy is being released, it's exothermic. That's just, you just kind of know. And we know that the Q of the solution is positive because it is gaining temperature and heat. 41C.